Okay, so I'm delighted to present Phil Rowe of Forestry England, who's going to talk about Pickering. We've got Paul Quinn of the University of Newcastle, who's going to talk about Belford in Northumberland, and we've got Hugh Thomas, who's from Forest Research, who's going to talk to us about natural flood management in a more general way. And we've worked with Hugh quite a lot in the past, and he's great. What else do I need to mention? Oh yeah, I should also mention this was supposed to be a bus trip to Pickering last May, and then another bus trip to Belford, Northumberland, which seems like a lifetime ago. And unfortunately, neither of those things happened, but here we are. So I'm going to hand over now to Hugh. Hugh, when you're ready, if you want to unmute yourself and share your screen. And do put questions in the chat, folks, as we go, and I'll collect them up for the end.
Good evening, everybody. Can you see my screen to start with? Yeah. Cool. I'm Hugh Thomas. I am a hydrologist and a project manager for Forest Research's Natural Flood Management Programme. I don't know if you know who Forest Research are, but we are the Great Britain's principal research agency in all things tree related. Used to be part of the Forestry Commission, but since devolution we've become more of a separate entity, but we still work closely with Forestry England and Scotland and Natural Resources Wales, as well as organisations like Cumbria Woodlands. About myself, I worked for Forest Research for about 20 odd years, and been working on natural flood management since then, and it's been quite nice to follow it from a concept to what it is now, a kind of generally accepted method of flood remediation. I'll just go through what I had planned today, which was to just very brief overview of how woodland contributes to natural flood management and how it interacts. Those are my contact details at the bottom if anybody wants to get in touch afterwards. I've been involved in a number of big projects over the years. The one that came up first was the Ripon multi-objective project, and that looked at various opportunities to reduce flooding using natural flood management at a catchment scale in Ripon. I was going to say a little bit more recently, but Slowing the Flow is about 12 years old by now, I think. But I've been working on Slowing the Flow and still do. And that was a project to work with nature to try and store more water in the landscape and slow the passage downstream by using natural flood management. Part of that was some woodland planting, large would be debris dams in the catchment, some storage reservoirs, and some more localized farm scale measures. Phil will go over Slowing the Flow in a lot more detail later on. But yeah, it's been a project that I've been heavily involved with over the years, and it's been great to follow it through. So how can woodland contribute to flood risk? It's generally recognised, it's well documented that woodland can contribute a great deal to reducing flood risk in the catchment. The main mechanisms are that it reduces volume of flood water by increasing evaporation from the tree canopy itself. Secondly, it slows the rate of runoff from the land. It's been measured with lots of research being done to show that it increases soil infiltration. It enhances floodplain storage, delays flood peaks, and woodland has a higher hydraulic roughness, they call it, so it's more effective at holding floodwaters back as when it enters the floodplain, when it flows out of bank. And it also reduces sediment delivery and siltation, and that increases conveyance. The catchment can hold a lot more water. I wouldn't be a scientist if I didn't show some graphs for you. This is been a well used graph by now to show how conifer and broadleaf differ in terms of annual interception losses. Conifers have been measured to intercept up to 25 to 45% of rainfall. Broadleaf is a bit lower, from 15 to 25% of rainfall. And a little table in the corner there to show the differences between woodland, grassland, heather, bracken, arable, and conifer especially sits there with the highest in terms of interception, transpiration, and total evaporation. So it has a big impact on the amount of rainfall that reaches the ground and the stream network in the catchment. Second one enhances soil infiltration, and the woodland acts as a sponge because the root systems of trees break up the soil structure. There's large pathways down through the soil because of roots, compared to things like grassland, especially when it's been overgrazed. Another graph there to show some measurements that were done a number of years ago, looking at infiltration across a transect between grazed and planted woodland, and it was showing up to 60 times soil infiltration at the time. Not the details, but this is a very old table of figures to show the hydraulic roughness of woodland and how it can be a barrier to flood flows. When you get down to figures for trees and woodland, it can be up to 5 times as hydraulically rough. So it's a really effective natural barrier to flood flows across floodplains. There's a very early piece of work they did down in Somerset. There's two-dimensional hydraulic modelling just to show how flood flows are affected by placing woodland on instead of grassland. Then, so the top one shows the river system in flood on pasture, and the bottom one shows that when you place woodland on a floodplain, you get much slower, much lower velocities across the floodplain, and as a result, the water levels increase. It increases storage, and we were seeing in the model that the storage was increased by about 70%, and it also delays the flood peak as it travels downstream. This isn't, I've done a lot of computer modelling over the years, but it is actually measurable in terms of the real events. This was one particular one that we managed to measure was the Boxing Day storm in 2015 in Pickering. And we compared the rainfall to previous rainfall events before the measures were put in place as part of the Slowing the Flow project. You can see there we picked out an event in 2009 which was comparable to the December one. We were seeing that there was a 18% reduction in peak flows from solar storm events because of the natural flood management measures that have been put in place. and a 1.5 hour increase in lifetime. So it's not just modelled, it is actually measurable in certain cases, which is really promising, and it's something that has been taken forward to certainly gives a strong case for using natural flood management instead of more traditional engineered approaches to flood defence. And it's I can't see it replacing engineered defences, but it's certainly complementary, and it can reduce the reliance on it, and certainly take the edge off things for climate change, and to help things with that. On the other hand, woodland can increase the flood risk in certain areas if it's in the wrong place. It backs up, it causes a backup of water, and no denying that. So if there are assets and sensitive areas upstream, there is a potential to increase flood risk. We always see bridges with trees trapped underneath them in the news during the floods. But what we don't see is that the water still goes underneath the bridge and wood tends to float. So it's not as bad as the media make out sometimes, but still it is an issue. And the other one that woodland can cause is synchronization. We always talk about that it can desynchronize flood peaks in certain areas, which can reduces flood peaks, but it can have the opposite effect. It can actually in the wrong place. It can synchronize flood flows between two river systems and make things a lot worse. So you have to be careful where we place woodland and natural flood management measures. Yeah, we've just got to be conscious about where we put it. This is add on if I've got some time to look at a bit more at large woody structures, or there's a load of other terms that you can use to describe the same thing. It's essentially a leaky woody dam in the watercourse, and it effectively holds water back and delays the passage of flood flows through a river system. And we tend to see these naturally forming in sequence, so that you might see several of them as you move downstream. And what we've done in places like Pickering is we've tried to mimic that natural build-up of woody material. And those two are quite nice ones in Pickering, and they actually have photographs of it during a flood, and you can see how well they hold back flood water. And if you have a series of these, the volume can be quite considerable. My attempt at a bit of art there to show what happens during a flood, behind and downstream of a woody debris dam, and that's the top and bottom photos there, the same dam, one during normal flows and one during higher flows. So what generally happens is the water backs up behind, and you still get through flow through the gaps in the timbers. Fish and things can get through. You get a shallow plunge pool at the bottom, the downstream end, and we've carried out some electrofishing surveys at some of these in site in Wales, and this fish actually use these timber dams for feeding, for resting. Yeah, they are definitely not a block, kind of a barrier to them. Yeah, so that's how woody structure works. It clearly shows it's not a complete barrier to flood flow. It's really leaky. It's just a few conclusions. So there's a strong understanding of the processes involved with trees and woodlands and how forests can affect flood flows. There's a lot of modelling studies out there, and a lot more actual kind of fieldwork based studies now as time goes on, which is what we really aim for, is to test these systems to give people hard evidence that they work. As I said, the location is very important, and you've got to be aware of the risk involved, to not make things worse in a catchment. The aim is to make things better for people. So that's a very brief introduction to woodland and natural flood management. So I find that useful.
Thanks so much, Hugh.
Pleasure.
There, that was great, and spot on with your timing there. Yeah, so you've set the bar, I'm afraid. We've got 3 questions so far in the chat box, so we'll collect those for the end. Is anybody unsure about where the chat box is? Just along the bottom bar of your screen, of your Zoom screen, you've got options to react and an option to contribute to the chat. There's a little speech bubble in the chat. So make a note yourself, or put it in the chat box as you wish. Okay, we're going to move on now to Paul, who's going to talk to us about real life example. Thanks, Paul.
Just loading up. Can everybody see that? So basically this is I've sent a PDF of this. It's quite a lot of detail as we go through, and I'll just be skipping over, so you can go back and have a more detailed look at the images and graphs later on. But my background is actually in agriculture. I am a hydrologist, but working on farm pollution. And so I said, oh, surely sediment traps and ponds and wetlands would be the best way of removing phosphorus and sediment pesticide. And I did a lot of work in that. And then somebody said, well, would this work for floods? And I said, yes, but it'll cost you, you know. And so at our various research farms, we just said, okay. And I built lots of big ponds and lots of big woody structures. And people then said, well, do you want to try this for real on a village of Belford, which has been flooded 7 times in 7 years, and it needs to be sorted. Okay, so you hear lots of terms. You use lots of terms. There's lots of other terms out there now. So you've probably heard of the dreaded nature-based solutions. That's the term we're all using now because it's in COP26. I'm in the School of Engineering at Newcastle University. So this title of catchment systems engineering is deliberate. We all live in catchments. Yeah, that's where we live. And we want to have our food and our water, our recreation, and live somewhere safe. Okay, we don't want floods, we don't want droughts. And therefore, the system is the catchment. And the system is malfunctioning. We have too much runoff and too much pollution. There's too much energy in our systems due to long-term changes. And this is happening all over the world. And so I say engineering in the loosest sense, because we do soft engineering. We are mimicking nature. You know, think of nature as an engineer, engineering the landscape. But the one thing that we are, because we're engineers, is interventionist. We go in and we change things. We're trying to bring back balance, but we can't go back to 100% trees. We're going to have our food and our places to live. So thanks to many, many people who have helped me over the years there. I'll just jump through a few images. They're all pretty obvious what's happening. So let me just get rid of myself off the screen so I can see what's there. So this is supposed to be like a post-war landscape. We'd already changed the function of the landscape, but after lots of other changes, we've now got a very well connected and perfect runoff scenario. So if you add any climate change on that, then basically we're in big trouble, and we're in big trouble. So there's lots of reviews on this. The government did a review of this and concluded that farming contributes to flooding. If I just take one of our friends up in Scotland here, I always say, go and look at the oldest map you can find of your area. This is up in Tarland, near Aberdeen. And this is what it used to look like, nice braided rivers. And then we had the great farming period, and it was all replaced with land drains and dikes. And more recently, a lot of the land drains are now buried, but they are still there. And we have these perfect runoff catchments. We've also done a lot to our soil. You can't grow a crop in anoxic soil, so we put land drains in, we've got a lot of clay in our landscapes, and we've been degrading our soil for 200 years. And so we don't really have soil anymore, we just have a media in which we grow our crops. So you just add water and nutrients and you can get a crop. So we're now prone to less storage in the soil and overland flow. So as Hugh says, any planting or the biggest decision we make is just not to have a crop. It's just brilliant for the soil and for the canopy. But my take on all this is that I work with a lot of people who are very skeptical about NFM and have been for years. And it's taken a long time for us as a community to prove that it's worth doing. So I'm trying to work on the worst case scenario, which is the biggest storm, Storm Desmond type storms, and it's been raining for days and everything's saturated. So the interception is not there and the soil storage is not there, and it's still going to have runoff. And this, as we say, the system is prone to losses. So just one example of a feature in Belford. And so we engineer these things called runoff attenuation features, which are ponds in which you can grow a crop. But in this case, it's just a headland, sorry, a buffer strip. And you can't actually see, but there's a bund in there. It'll become apparent immediate. So our little mantra is slow store filter, which I think is commonly used now. And so we can put a barrier in to stop overland flow. That sounds good. But if you also redirect water, where this little person is over here, you can actually redirect peak flow offline. So this is what we call an offline feature, and it traps tremendously large amounts of sediment. And so in the catchment of Belford, poor old Belford down here, getting flooded 7 times in 7 years, because we're just going through a wet period. And during the time when we instrumented this catchment, we had 4 1 in 100, if I could say it, 4 in 1 in 100 year floods, 4 enormous floods. And we were very, very lucky to have them. And fortunately, we've done enough interventions to stop those floods flooding Belford. So they were quite happy, including Storm Desmond. And we've got lots of, so some things target overland flow. And we've obviously used some woody debris barriers where we could. And we've got a mixture of ponds. And here's an example of one, a random appearance of some wood in the middle of a field, because we know that there's a big overland flow pathway down here. And this is just after a storm. It fills up to the top, and at the far end here, the furthest away from the river, is where the water spills and goes back. Yeah, just get them in the right order. Here's another one with a big bund in the middle of an arable field. And you can see for scale, my 2 colleagues there, and you can see we've got a pipe, very big pipe in the middle, but this is made out of local material. And this is what it looks like during the storm. So we've actually built it as a bridge. So the farmer gets an appreciation of this because they don't have to traffic through. And we captured about a ton of sediment in one event here. So you can see what we're up to. And obviously the obligatory woody debris. I work with some guys now who insist that all your woody debris should be living features. So we now try and plant them up with other things. And then chop down a few sycamores that the EA didn't seem to like, but then we replaced them with more ash and oak. And you can see we did the trick that Hugh mentioned of putting anything we can across the floodplain for the roughness. So it's win-win-win. We had a forestry ditch, one of these old time forestry ditches. You can see the young conifers in here. And we just put lots and lots of engineered dams. So it's a bit dead. So I probably wouldn't do it like that now. But being a scientist, we've actually studied these features in great detail and know everything about them, how much water goes in, how much water is in the feature, and how much water comes out. So if we had just one pond, in this case, 560 meters cubed, and we know at what height the water came in, if you put a very big storm, this is an enormous 1 in 100 year storm that came through Belford, one pond makes no difference. Okay. So then the question is, well, how many ponds do you need? How many features do you need before you can convince somebody that you're actually having an effect? And that's why it has to work at the whole catchment. So another interesting thing here is you can see why it floods in Belford. You know, when the soil's full, the canopy is full, and the drains are full, you're not flooding. But the moment you cross this point, you get rivers of overland flow, and then it causes peak for it to drop. So one pond, tiny effect. So if we know exactly how one pond worked, then we can start to play with the models and sort of say, well, what configurations of storage and flow would affect the peak? And this is what we've come up with. So the blue line here is the original storm that we measured. And this is probably our biggest storm. And you can see that when we put 5 ponds in, there's still no effect. 10 ponds, still no effect. In fact, it's not until we get 15 ponds do we see an impact. But after that, every pond you add has a really significant effect on the flow. And you can see it being displaced into the recession there. So this is our basis. We've run all sorts of models on this, but this is just the kind of the simplest one to get across to people, that the more you invest, the more features you have, the more likely it is to work. Okay. Another place in Northeast Netherton. So here we have a bit of a synchronization issue in that we have a big moorland here that tends to produce huge amounts of runoff, and it comes down through this lowland area. And it was very difficult to do any work in the uplands. So we've put lots and lots of features in the lowlands, including an enormous network of features on the floodplain here. So there was a danger that if we delayed the flow a little bit, it might synchronize with this. So we've had to design the lowland features to really, really slow the flow, so that this peak comes down and gets processed first. But the thing here, the difference between this and Belford is this big wetland, this big floodplain. Hey. And this is what we planned. So we've got one feature here, which is a big pond coming from agricultural land. And we have this floodplain here where we tapped water off, and it went through a whole series of swales and ponds before it returned. And we did some observations to try and get the right draw-off level. And this is the draw-off feature at the top. So a digger man dug out nearly 200 meters of, nearly 200 meters of swale before it connected into a glacial channel that's been there forever. Well, not forever, 10,000 years. And then we'll use that. This little feature here is a bund and a pipe to stop water disappearing back into the river. So it keeps it on the floodplain. A little bit of engineering. And we put a series of bunds in, and it's actually a bund there. You probably can't see it. I'm going to have to highlight it for you. And that was made from the spare material that we had from a pond downstream. And then the water leaked out here and then leaked back. And then the farmer insisted on having a pond. So we put one in, and we were told by the EA to put a little island in, and here you can go fishing. But we then took the advantage of putting a 1 meter bund all the way around it. And we took another option to say, if you want this pond not to fill it with sediment immediately from your arable land, you're going to need some sediment traps. And this is how it, when it's full, it overflows. And here you can see after 1 year, the amount of sediment we're capturing. So the farmer is paid in the scheme to come and remove that. I'm not sure if he has yet, though. That's about 3 years ago. And just to show that there's a lot of information on here, but basically those 3 ponds take out about 50% of the sediment, 30% of the phosphorus, and we were surprised it even took out some nitrate. And it wasn't designed to take out any nitrate. And one other site up at Wallington Estate with National Trust, they wanted to improve their carbon credentials by putting a wetland in, and we found this site with a channel running down here. You can see a historical channel running through there just about, and there's another channel coming down here. So it was a no-brainer to say, well, let's put your wetland in. Let's make sure it's accumulating carbon. But once like this, you think, let's get bund in. So we put a really long bund along here to back up all the water. And that's the bund. And then we put a draw-off feature here, similar to the previous one. It's just to take flood flow. So it should only trigger 10 times a year. And then there's a dirty drain coming down here. So we've put settings for that. So it's a kind of a perfect location for lots of hits. And then when it's really full, it's really full. We can't even work out how much water's in there. It's that tricky. And that's the new flooded area. So we think we get all the multiple benefits. And there's the little draw-off feature, you know, it's cheap as chips. You know, we've monitored it for a while to see how high the water would get. And then we've got this draw-off level here. And it flows off for nearly 400 meters down to the bottom end. This is the bottom end with a nice digger. Let's put this beautiful bund in. You wouldn't even know it was there now. I should show you with the scour protection at the outfall. And then I think this is what Hugh was getting at. You kind of, if you put all these things together, then you get what we call a treatment train or a catchment system engineering plan. So in local places, you can do small interventions. You can even do some pollution management on the farms, buffer strips, cascades of ponds, draw-off channels, woody debris. I think you use that photograph, and lots of these ponds. And then you put them together, and so you change your features as you move down. And if you can get down to a floodplain, you can either afforest it or you can put some offline ponds in it. So we're working on the assumption that you can do most of the environmental work that we need in the smaller parts of the catchment. It's nice to work on the big floodplains, but there's usually houses there, railways and other infrastructure. So what we need to convince people that third order, fourth order streams and upstream of that, especially the ditches are perfect for management. So a little very general conclusion here is that we're pushing elms and other things to try and apportion some land that should be taken out of production so we can put in the wetlands and the buffer strips and the forestry zones. But we probably need another 5% of land for temporary storage. So we'd like farmers to be paid to temporarily hold flood flow, but most of the time it's just farmland. And that's really all I wanted to say. I'll leave you with that.
Thanks very much, Paul, and some really marvellous photographs there. Phil, if you'd like to introduce yourself and unmute. And when you're ready, share your screen.
Hi. Let's share screen. Can't see the. Share the screen button, Claire.
If you just go to the bottom of your Zoom window.
Oh yeah, got it.
Yeah. That looks perfect.
Yep. Okay. All right. Good everyone. My name's Phil Rowe. Yeah, I'm a forester with Forestry England over in Yorkshire, a local coordinator for the Slowing the Flow project. Tonight, I'll just give you sort of a background to the project, the measures under operation, the current status of the project and where we're likely to be going in the future. So yeah, Pickering's got a long history of flood events. The bridges tend to be the pinch points that once they're sort of engulfed, then the town gets flooded. So the location of the project has been really across two catchments, River Severn and the Pickering Beck catchment. One of the interesting things is obviously it's a catchment scale approach, and it's notable that both of the catchments are actually less than 100 square kilometres in area, which has some significance in terms of data collection and sort of proof of results, etc. We can probably discuss that later even. Nature of flood events, as sort of Paul alluded to, is the floodplain tends to remain dry during flood events. Obviously the long history of the river channel coming in size, linear, cut off from the floodplain, so the water discharges very quickly to the town. Also the scale of the damage as well, which is reflected, I suppose, across the UK during other flood events. The project itself was set up in 2009. It was very much a partnership. Agencies were tasked to work in partnership with a very much a focus on NFM measures. The original objectives was a demonstration of these. They were sort of to cover 7 areas. So it was debris dams, riparian woodland, farm woodland, and then there was wider kind of emphasis put on blocking moorland drains, looking at forest drainage, reviewing felling plans, carrying out measures at farm scale on farm yards, etc. And all this was to complement the construction of an engineered bund just outside the town of Pickering. The actual areas themselves, we're looking there at the Pickering catchment. We're very much working with large landowners, so the North York Moors National Park, the Forestry Commission and the Duchy of Lancaster. That's like a key thing for us, was the involvement of large landowners. Also, the correct placement of the NFM measures, as you both Paul have alluded to. We have a little map there of the key placement idea and the synchronizing and desynchronizing effects. Very much the sort of the lower third of the catchment with issues if you sort of place your measures within the red tributaries that are shown there, for example. The woody dams that were installed and the timber bunds, a total of around about 170 dams installed across the two catchments, with a volume of storage. Very much cost effectiveness issues coming in there, evolving robust design, the design becoming more secure, and then working with a maximum channel width of about 5 meters, where the Forestry Commission also took it upon itself to install 2 timber bunds at the time as well. So these are extremely cost effective in terms of construction costing, and they do have long-term issues of longevity and also responsibility for upkeep, etc., moving forward. So these are all questions that get thrown up. As far as dam design, we've had a chance to evolve dam design over time. We've fine-tuned from the debris dam approach to the more now sort of stack log secured post and brace kind of structure that allows the dam to kick in at a certain level of the flood event, and obviously fish movements unimpeded. So there's all this sort of refinements connected with that. The wide efforts that were carried out, the objectives, again, a range of farm woodland, riparian woodland, the large bund, the moorland measures, all sort of contributing, felling planning, farm management, all contributing to a volume water storage, where we have a total for natural and a total for engineered. And within the project, NFM contributing to around about 10% as an approximation. Findings from the models, as people mentioned, the roughness, the prediction of a 1 in 25 year event reducing flood peak by around 4%. So on their own, the measures wouldn't protect Pickering from that level of event, but they can make a contribution to flood flows. The Boxing Day event that was mentioned, it was quite interesting that the NFM measures and the engineered measures together, well, the NFM measures contributed to around 50% of that reduction. So like a 2 cubic meters a second reduction, half of it was through the NFM measures. Probably Hugh might be able to sort of answer this, but they probably would have been overrun during larger events. So it's the level of event on that particular Boxing Day that they worked really well, but they probably would stop working after a larger event. Monitoring continues, as Hugh says. We have 10 collection points within the project, so there's also annual dam surveys done to check for if there's any maintenance or repair issues required. Some of the costs that were involved, so there were considerable costs, but I suppose it acts as demonstration for the rest of us, and it's got a lot of those were actually realised. So maintaining those, yeah, channel intervention requires regular checking and maintenance, as we mentioned, and the more dams you have, the less risk there is of debris moving downstream. So one particular event, there was damage to 11 dams, and so there was replacement costs involved. And these costs are key to sort of future thinking in terms of calculations on where we might go and how much we might be willing to spend. So where we're at, phase 1 and 2, phase 1 the NFM, phase 2 the main bund, and now we're into phase 3, as we say, driven by some of that cost calculation that was involved, and a lot of things coming to fruition at the same time, and allowed us to sort of think about using beavers. So we have a 5-year license, and we're working with a set of objectives with the beavers in the River Severn catchment. They're not in the Pickering Beck catchment, so they're actually in the River Severn catchment. They are in an enclosed area of about 9 hectares, so it's got about a mile's worth of fencing around it. It's got one of the timber bunds that we've sort of saw earlier is actually incorporated inside the area, and the beavers were introduced to these kind of ponded areas up here. It's sort of like these dry beds that there were at the time. So and this is just the impact that they've had over 2 years. The ponded area, they've now created a kind of a 60-metre dam across the top of that kind of area, and they've connected the Sutherland Beck to the right-hand side of it with a 2-metre high dam in the stream channel. So they've now connected that whole top area as their living quarters, so to speak. We'll just have a look at a sequence of the current impact. So this was before release. This was just May 19. The beavers have been released a month earlier. This was in December 19. This is August 20. And we're now into December 20 here. So they've now almost they're now sort of it's almost like a third of the site is now sort of being managed within a 2-year period. So the work continues. We are at the moment, it's this year. 2 of the kits from the 19 family will be probably trapped and moved on to other projects. Interesting there, I put a Dor Benton's bat in. That's the first time that's ever been seen for a very long time in the area. So the habitat diversity is actually taking off big time. The Hydrological Process is my journal there. It's sort of looking at over 1,000 flood events based on beaver interaction, and that's moving in a positive direction. The village of Sennington itself, which sits down below on the River Severn, below the timber bunds and 33 debris dams plus the beaver enclosure, it also has a further 69 natural blockages within the channel system as well. So the future for Sennington, it being totally based on natural measures, is looking quite good. So that's where we are at the moment. That concludes it, really.
Brilliant. Thanks, Phil. So for those that don't know, I grew up just near that site. I grew up in Scarborough, which is near Pickering, and I never imagined that Dalby Forest would look like a Canadian muskeg from the air. That's very, very exciting, really interesting. Right, we're going to go straight into the questions now, I'll go through the chat questions first. Do you want to stop sharing your screen, Phil? There you go. And of course, if you've got any questions, just raise your hand using your real hand or using the reaction emoticon at the bottom of the screen for me. Okay, first question is a technical question instigated by Juliet Merrifield about one of Hugh's charts, and it's about broadleafs versus broadleaf trees versus grass. I don't know if that's roughness or storage, but Juliet would like to know how they compare.
Yeah, so the question is showing that broadleaf can be is not much better than grassland. It's an average over the year. So you've got to account for when the trees aren't in leaf. So the effect is markedly reduced during the winter for broadleaves. But in the summer, it's much higher than grass. So grass is going to be more constant throughout the year. Broadleaves is more seasonally variable.
Thanks, Hugh. And that leads on to Dean's question, and that was about the seasonal difference between interception of conifers and broadleaves. So I think I've answered that. Are you happy, Dean? That's been answered. The second half of this question is about drought in the southeast and tree planting. Does anyone want to come in on that?
In terms of our research, we haven't started looking at the effect that these natural flood management measures or woodland planting can have an effect on drought or help drought in any way. But it is something that is in the pipeline, which I hope.
Can I comment on that one?
Go ahead.
So, first of all, people are saying, obviously, the water yield from catchments goes down compared between a forest and a grass. I did my PhD on Plinlimmon. It's very clear, I think. And my magic number was 29.5% difference in runoff, thanks to the forest. But this idea of catchment systems engineering, we already know we're losing too much water. Okay, so all the water we lose is going straight to the sea. That's not doing us any good. So we need to keep that water back. So fixing them all, fixing the agriculture, doing riparian management is what we need. So who knows whether the forest is really making things a problem. Unless, of course, you design it in. You design it in so that your woody debris and your forest holds enough water for long enough that it goes into the ground. And in one study with Dave Brown and Mike Norbury over in Greater Manchester area, they're picking this up on their base load. They're seeing that water is going into the ground and it's reappearing later. And I would think, because it's a catchment system, slowing down your water, and we've done this in Rajasthan, I know it's not very relevant to here, but we've got 15,000 ponds in Rajasthan holding the monsoon and getting it into the ground. So in principle, you have to design in not only slowing the flow, but design in the residence time to get the water into the ground.
Yeah, I just say that's what we'd all hope for. But it would just be nice to have some evidence to use as a helpful ammunition for that. I mean, I've worked with other projects which are using pretty much the same techniques of leaky woody dams and things to drive the water. It's infiltration and going down. I just wondered if it was the argument that occurred to me that if what you're doing is increasing interception and evaporation straight back up, that's actually a loss before it gets in. So, but it's not going to stop me making planting trees.
No, but I mean, that process is still occurring and is increasing. But when it rains, it will always overcome the canopy storage and there will be surplus water around. So what you need to define is, when is there surplus water around? If there's surplus water around, hold it in the system. That's the way nature wanted it.
Thanks, Paul, and thanks, Dean. And then there was a further question from Dean about synchronization. I don't know if everyone's comfortable with that concept, but thinking about when a river peaks, and then if you get a tributary meeting another river, they're going to have different peaks depending on the track of the storm, on the nature of that catchment, and you might accidentally slow one down that then adds to another one, and you make a flood peak somewhere worse. So Dean acknowledges it's a theoretical, graphical possibility. Any real world examples? I'm pretty sure there are in Cumbria.
There's one, the one I worked with, the Ripton project. Britain gets flooded from synchronized flood peaks from the lava and the scale. So it actually happens, but it's not it happens naturally, not due to kind of interventions up in the catchment. But yeah, it's caused by synchronized flood peaks, and I think a lot of.
I think most systems are vulnerable to synchronization, but there's two really big issues. One, which direction is your storm coming from? Okay, so in Pickering, you've got this north-south pattern. So if the storm comes from the north and travels south, it gets a very different result if the storm comes from the south and travels north. The next problem is, if you're defending Pickering, well, what about Sinnington? What about somewhere downstream of Pickering? So if you design for one location, you may not be sensitive to other locations. So we set up a little model to play this. We kind of gamed it to show different storm tracks, different interventions, doing one subcatchment, not doing the other. All right. And there are synchronization, but the way you can fix that is to do NFM in all the catchments. Everywhere should get slowed down. That's the safest solution.
Yeah, I agree with that. I mean, I had a little bit of resistance to doing any FM at all from some people in some places. Oh, what about synchronization? And you can't proceed before you've done, you know, masses and masses of modeling to do anything. And we've got they're fairly simple catchments. They're not kind of highly branched ones with two obvious things. So looking at it, common sense ought to tell you, well, it shouldn't be a problem. But the other thing is, if you're just slowing it down everywhere and holding back and absorbing it, it's unlikely. Chris Utley described it to me once as the chance of it happening by what you're doing in a particular storm. It's like firing two bullets at each other and expecting them to hit. So although it's there, the probabilities of doing stuff that's slowing it down, they're making the problem worse, are smaller than your probability of improving things.
Our case study was actually Great Ayton. Don't know if you know Great Ayton site. We didn't have enough money to put many features in, but we were able to build this model to show the nature of the synchronization. So it's based on some real data. So people are welcome to that. People can have a copy of that. It's like a little education tool.
Thanks, Paul. Thanks, Dean. That's great. So we're all a lot more familiar with the limitations of modelling than we were 18 months ago, but it is worth doing a little bit of modelling, I think. Juliet, again, doesn't sound like Juliet's got a lot of space. So what can we do if there's not a lot of space in the catchment? Does anyone want to come in on that?
So my point would be that when the flood's coming, you'll see water everywhere. It won't be coming out of the ground. It'll be moving over the surface. So that's when I showed that example of why does Belford flood? It's when there's water on the surface. So we were able to then say we need to target these temporary flow paths. Now, I'm not sure what Juliet's situation is, but maybe there's buried drains that could be daylighted. Maybe there's only a small amount of space. Well, make use of that space. And then, you know, probably people live in the wrong place. So you have to go upstream, and you may need a traditional defense, but I'm sure that if it's farmland or forest upstream, there's opportunities to store flow in the big storms because it will be on the surface.
Juliet, do you want to come in on that? Don't have to, but.
Yeah, I think that's helpful. I mean, we're living from the edge of our village to the slope of the South Downs. It's about a mile, so we are really constrained by space, and the water comes pouring out of the aquifer under the downs through spring and you know, seasonal streams and so on. We've been working with some woodland owners and trying to persuade our local council that some of their land could take seasonal ponds and so on. But they're, you know, we're in the southeast. We have huge pressure for housing. We've got small farms. We don't have, you know, a big landowner who you can get on board. So it feels very much more constrained than what you were able to do there. But we're doing what we can do.
If you've got true groundwater flooding, then it's very difficult to manage. Other than moving, you probably don't want to do. But as I say, in the flashier elements coming off the moors, they will contribute. So you'll have a worse flood if you've got surface water and groundwater. So you try and manage the surface water. That would be an obvious thing.
Yeah. Yeah.
I'm not far away from Julia over in East Sussex, and I'm familiar with some of the flooding from off the downs from previous experience. And I think, like you say, if the whole thing is saturated and you get these sudden summer thunderstorm or whatever, the amount of water that's actually running over the surface on the steep slopes really quickly is a big kind of contributor. And those seem to me the perfect place to be putting bunds at the bottom of the slopes and other things. And to, there may be possibilities on a normal day. You look at it and you think, well, there's no water there, so how can it be a problem? But yeah, I think one of the best tips I've kind of got is if you're trying to do this stuff, when it's really, really chucking down with rain, go out and have a look.
Go for a walk
and see where the water goes. And it really opens your eyes, because most of us shelter away from it, but do the opposite. It's great. Thanks,
everyone. That's brilliant. Okay, we've got one last question before we finish from Edward Wilson. Ted, do you want to pose your question? It's about beavers.
Yeah, I'll just put on my video there. Yeah, thanks. That was a fantastic session. So much information in a short time. Yeah, I'm fascinated, Phil, with your beaver experience. Given that they're in a confined space and they're expanding the pond, does that not mean they're eating out all of the trees and vegetation? What's the implication there? I think that was my question. Yeah.
Again, an ecologist would give you the definitive answer, but the one I always fall back to is the kind of the experiment they've been doing down in with the Essex Wildlife Trust with the river otter and the enclosed trail they've got there. It's a much smaller area. It's probably no more than a hectare even, and it's it's only a couple 100 meters in length. It's been probably going into 12 to 10 years of kind of data collection from there, but they've never been within. They've never ventured more than 5 meters away from the channel towards the fence in all of that time.
Wow.
We have the same thing as well. We've, under our license, we had to sort of jump through a lot of hoops in terms of we've got a Colditz fence with a skirt, and the downstream and the upstream kind of engineered grates and grills and all that is all in place. And I think from a behavioral point of view for the species, it's just it doesn't happen. The only way they'll explore is if they're going up a stream, and all the kind of side channels that we have to the enclosure, they've all got skirts and blockages in the way, etc. So if they eventually do want to travel, that's as far as they can go. I know that on the River Otter, they have ventured right to the top of the catchment of the River Otter, almost onto the top going into Somerset. So they will travel within the watercourse system. That's where they live, basically. So we're happy with it. In terms of them, the food supply is perfect for them within the enclosure. So they've got the right stuff. We've got a lot of sacrificial material in there. We've got the mature broadleaves that we want to protect. So all that's protected. We've got conifer elements, rhododendron elements that are sort of there to sacrifice as well. I think in terms of a structure and a behavior of a family population moving forward over time, I think some animals will have to leave the enclosure. And I think you do eventually get to a situation where you end up with a beaver lawn, and the beaver lawn almost works its way as a step terrace down a system. So who knows, in the next decade or so, we may have different thought processes from a country's point of view in terms of how we feel about all of this, and whether this, whether we still need to enclose them, or there's a possibility of a wider kind of distribution of them within the catchments. So yeah.
Okay, thanks.
Thanks for your question, Edward. Cheers, Phil. That's great. Thanks so much, everybody. We're going to close up now. Do keep in touch with Cumbria Woodlands. We'll be starting our events again in the autumn. So keep an eye on our social feeds and sign up for our newsletter. Thanks very much for coming. It's great to see you all. Enjoy the rest of your evening.
Thanks. Bye.
Bye.